Welcome to Secret Squared. I'm Cassie Secret. I'm Megan Secret, and today we're going to start a new series on factoring. There are a lot of types of factoring polynomials. We are going to focus on factoring by the GCF today. So let's dive in. So before we actually factor by the GCF, we're going to see what factoring polynomials actually means and what the GCF is. So when we factor a polynomial, that is pretty much saying we are taking an expression, we are rewriting it, and we're making it or turning it into a product. Reminder, product really just means that you multiply things. So at the end, we're going to end up with two things or maybe several things multiplied together that are the same thing as the expression, it's just written a little bit differently. So oftentimes what you're going to end up having is when you finish factoring a polynomial, you'll have like several sets of parentheses with stuff in it that's indicating it's being multiplied. Now, when we're talking about factoring by GCF, GCF should be a common term that you've heard before. It stands for the greatest common factor. Now, that phrase can be kind of overwhelming, but just breaking it down, what the greatest common factor is, it is the biggest. That is why we have it as the greatest common factor. It's the biggest, and it's the biggest thing that divides all of our terms. So what that means, the greatest is telling us that we need the biggest thing of something. What a factor is something that divides something. So like a factor of 10, like 5 is a factor of 10 because 5 divides into 10. So what we also have is we have common. Now, something that's in common is being shared by several things. That GCF has to divide all of the terms. So that's just breaking it down so we understand what GCF means better. So before we look at GCF with some variables, we are going to focus on it with just some numbers. So let's say we're looking for the GCF of 6 and 15. Now, this should be a question that you have probably seen before, but it might have been a while. So when we're looking at the GCF, we want to find the biggest number that goes into 6 and goes into 15. Another way to think about it is it's the biggest number that 6 and 15 can both be divided by. A really helpful way to break it down is go one number at a time, so the 6 and the 15. Since we want to know what's the biggest number that divides 6 and divides 15, it'd be helpful to know, hey, what numbers divide 6 and what numbers divide 15? So looking at 6, 1 always will go into all of the numbers, so 1 goes into 6, or 6 divided by 1 does give us a nice whole number. 6 is even, so we also have 2. 3 also works. And 6 also works. So right now we are writing the factors of 6, or the numbers that can divide 6. And if it helps you to think about, normally for this list, they come in pairs. 1 and 6 multiplied to give you 6. 2 and 3 multiplied also give you 6. 15, similar idea. We have 1 goes into it, or 15 divided by 1 gives us a whole number. It's not even, but 3 goes into it. 5 goes into it, and 15 also goes into it. Now, making this list is so incredibly helpful because now we know we want to find, first of all, the factors that are in common. So if we're looking at the factors or the numbers that show up on both lists, I have 1 shows up in both lists, so that's a common factor, but I also have 3 that shows up in both lists. Now, the way that you're going to want to decide from there is you're going to have to figure out what is the biggest number that's in common that is the biggest. So the biggest number that shows up in both lists is actually going to be the 3. So we're going to say that the GCF of 6 and 15 is going to be 3. 3 goes into both 6 and 15, and it's the biggest number that does this. A lot of the times 1 is normally an option, but typically there is a number a little bit bigger that also goes into those. But not always, so it just depends. So looking at another one, so let's say we're looking at 7 and 21. We're going to follow the same steps. We're just going to list all of the numbers that 7 can be divided by. And in this case, there's not a lot of numbers that do that. 1 goes into 7, 7 goes into 7. And then if you look at 21, we have 1 goes into 7, 1 goes into 21, 3 goes into 21, 7 goes into 21, and 21 also goes into 21. So then from here, once you have your list, you want to find the common factors. Now, 1 is always going to show up in both lists, but we also have 7. So we want to pick the greatest common factor, and that's going to end up being that 7. So our GCF is going to be 7. Now, just something important to note, sometimes that number is the exact same as one of the numbers you started with. In our first example over here, 3 is not one of the numbers we started with. It just depends on the problem. So now that we've looked a little bit at GCF for numbers, we're going to see how it works for variables, which is a little bit different, but honestly, it's almost easier. So for the GCF for variables, we still want to divide out. We want to see what the biggest thing that divides both of them, but we're looking at variables instead. So we want to divide out as many variables as we can from both the terms. Maybe there's more terms, but typically it's 2. And again, we want to take out as many variables as we can because GCF is telling us we want the biggest common factor. So we want to take out as much as we possibly can. And that's going to be a really important thing as we're looking at our examples. So for our first example with variables, let's say we're looking for the GCF of x squared and x to the 6th. Now, if you're looking at this, it can honestly be really kind of confusing because we were used to looking at numbers and now we have these variables. However, a really great recommendation and something that actually can make this process a lot easier is x squared. X squared is just telling you that you are multiplying x 2 times. So x squared is x times x, and x to the power of 6 is telling us that we're multiplying x 6 times. 4, 5, 6. And a way to think about it with variables is you are really looking at, this is still x squared, but it's broken down a bit. This is still x to the 6th, broken down. We want to see how many variables do both the terms have. There's 2, there's 6, and if we think we're dividing them out, we're taking them away. We're taking them away. And let's say, oh, there's 6 x's here. We could take 6 away, 5 away, 4 away, all the way down to 1. But over here, there are only 2 x's, so we can divide 2x away, but we can't divide any more than 2 out because the top doesn't have any more x's. So if we're thinking about, okay, what's the most amount of x's that I can take out from both the terms? I can take 1x out of both of them, and we're good, because they both have an x to take. I can go ahead and I can take another x from both of them, and I'm good. But if you want to take out any more x's than the 2 right here, you're going to run into a problem, because I don't have any more x's in that x squared. So what that's telling me is the most x's that I can take out they have in common is 2 x's, which we're going to end up writing as, so the GCF would be x squared. X times x, but really, that's going to be x squared. So another way to think about it is when you have it as, hey, I have 2 x's here, 6 x's here, how many can you take before there's not any more to take from one of the terms anymore? You can only take 2 from here. You can take 6 from the right, but there's not 6 to take from in the other term. So really breaking it down and seeing all of the letters written out can be super helpful. So another one that we're going to look at, and this one we're going to have, instead of just x's, we're going to do 2 different letters. Let's look at the GCF of, so a to the 4th, b, and a to the power of 6, and b squared. So we can do the same thing that we did up above where we fully write it out. Even though there's 2 variables, it just looks a little bit different. So we are going to have 4 a's, because it's a to the 4th, so 4 a's multiplied together, and 1b also multiplied on there. Because just a reminder that b has an invisible exponent of 1, so that's why there's only 1 of them. And then for the term on the right, it says a to the 6th, so we're going to have 6 a's, 3, 4, 5, 6 a's, and 2 b's. From here, we can focus on one variable at a time, so looking at just the a's. Right here we have 4 a's. Right here we have 6 a's. We want to think, how many can we take out from both of them? It is not possible to take out, let me make that clear, take out 5 or even 6 a's over here because there are only 4. So really, we're going to have 4 a's that we can take out or divide out of both terms. Yep, because again, I can take out 1 a, I can take out another a, I can take out a 3rd a, and a 4th a, but beyond that, you run out of a's in the left term, so you can't take out any more. So we have that part of our GCF. We have a to the power 4, and then you want to do the same thing, but now look at the next letter and look at your b. So we have 1b right here, we have 2 b's over here. It's a lot smaller number of b's, which is helpful. So we can try to pair them up. Here's 1b right here, 1b right there. But then once we take that or divide out that 1b, we are immediately out of b's on the left side. So we only can take 1b out. So our GCF is going to be that a to the 4th, because there's 4 a's we can take out of both terms. And then now we're just going to tag 1b on there. Yep, and then that is going to end up being the GCF for that one. So looking at another example for GCF for variables, we're going to see what happens if we have three variables. So we're going to look for the GCF of x times y squared times z, and we're going to look at x cubed y. Now, this is going to work exactly the same as the other examples, and it's going to start by us writing out all of the letters. So for the left term, we're going to have, there's no exponent, so really it's an x to the first and a z to the first. So we have 1x multiplied with 2y's multiplied with 1z. And then for the right term, we have a y to the first if it doesn't have the exponent. So we have 3x's multiplied together and 1y. And from there, we want to do the same thing as before. Remember our GCF for variables, we want to take out as many variables as we can. That's our goal. So let's go letter by letter. I can take one x out of each of them. However, if I try and take out any more x's, that left term doesn't have any more. So for our GCF, because we're just going to go ahead and do this in parts, the GCF is we have an x, and I'm going to go ahead and put the exponent of 1. You don't have to include it, but I'm going to. Then looking at our y's, I can take one y out of each of them. But if I try and take another y out, I can from the left, but the right one doesn't have a second y. So for my y's, I'm just stuck with y, and I'm going to write to exponent of 1. And if you look for the z's, so we have one z on the left side, we actually don't have any z's in that right term. Because of that, we can't take any z's out because there aren't any z's over here to grab from. So even though there are three variables, not all three variables are going to show up in our final answer. And actually later on, we're going to see some examples where you might have it, where your GCF, even though there are a bunch of letters in your terms, you might not end up having any variables in your GCF. It just depends on the problem. So actually our final answer for this one is the GCF is going to be x to the first times y to the first. So as we've been going through it, we've really been breaking everything up to show you, like, we just want to keep grabbing as many of a letter as we can from both terms, but we want to kind of explain what the rule is that you want to use, because sometimes it might not be as practical to stop and write out every single... Especially if maybe it's like an x to the 10th or x to the 11th. Exactly. It's too many. So what we're going to talk about is that's all going to get us to this rule that we tend to use when we're talking about taking out GCFs and when we have variables. So pretty much the rule is going to be when you have a bunch of variables, if a variable shows up in all the terms, you look at where it shows up and you're going to take the smallest exponent that it has. So for instance, for this one on this page, we had an x to the first and an x cubed. An x showed up in both terms. Because it showed up in both terms, the smallest exponent is at x to the first, so there ends up only being one x in the GCF instead of 3. And for the y's, I have y's that show up in both of the terms. So when they show up in all of the terms, you take the smallest exponent, which for the y's, that smallest exponent was 1. Because that smallest exponent is really telling you the smallest amount of y's that show up in one of the terms, and you can't grab any more y's than that. And then because the z did not show up in all of the terms, it's not going to be included in our final answer in the GCF. Exactly. So that's why we have the variable has to be in all terms. If the variable is not in all terms, like our z up here, then that letter does not get included in your GCF. So just be on the lookout for that. So now we're going to look at some GCF for terms that have numbers and letters together. So looking at it, we have the GCF of 2x times y squared and the GCF of 4x. Now, it might seem more difficult, however, it's just taking the pieces that we were already talking about, and now we're going to put them together. So we can start with ignoring the variables, and let's look at the 2 and the 4 and write down all of the numbers that go into it, or that can be that 2 and 4 divided by. Yep, so again, we're just starting by looking at those coefficients, and we want to write out the factors. 2 can be divided by 1 and 2, and then 4 can be divided by 1, 2, and 4. Now, the biggest number that shows up on both of these lists of factors is going to be that 2. So when we're looking at putting our GCF together, I know that I'm going to have that 2 as part of it. So that's dealing with those coefficients in front. And then looking at the variables, option 1, if you want to, you can write it out just like we did in the last page. Or using the rule, we can see, okay, we have an x in both terms. Because it shows up in both terms, it will show up in the GCF. And then we want to see both of them don't have an exponent written, so they're really an exponent of 1. We want to take the smallest exponents. So we're actually going to make it, they're both 1, that's the smallest, So we're going to have 1x in our final answer for the GCF. That came from here. And again, it's up to you if you want to write that invisible exponent 1 or not. We're just going to go ahead and put it just to remind you that it's there. And then the last part is we have a y squared in that left term, but there's no y term in this right term. So we are not going to have a y show up in our GCF as our answer because there's not a y to divide from both terms. So for that one, our GCF is just going to end up being that 2x. And then the last one, there are now 3 terms, which makes it a little bit more complicated, but a lot of the steps are the same. First things first is we have the 13 in the front, we have that coefficient of 13. We have a coefficient of 4. There is no coefficient or number in the front there. So what you can really think about is we have an invisible coefficient of 1. So just like we did before, we're going to take all of our coefficients. I have 13, I have 1, and I have 4. And we want to write out those factors. 13 can only be divided by 1 and 13. 1 is just 1, so only 1 goes into it, and 4 we already had from up above. So for this one, you're looking at the greatest or the biggest number that is in common on all of these lists, which there's actually, it's just 1. So let me fix that. And because the only thing that goes into 1 is 1, immediately we're stuck with that is the only possible thing. So a little shortcut that a lot of people like to use, if you ever see that one of the coefficients is 1, that actually automatically means that that number part of your GCF is going to have to be 1. So we have our 1 there, got that from our coefficients. And then from there, we can go variable by variable. First things first, we have an a squared, we have an a here, but there's no a in the right term. Because that a does not show up in all of the terms, it is not going to show up in our GCF. So we're going to skip a and go to the next letter. Looking at b, there's a b here, but there's not a b over here or over here. Same idea as the a. There's not going to be a b in our final answer of the GCF. Yep, that variable has to be in every single one of the terms. Now, looking at our next letter, I have a c in every single one of my terms. So that means I'm going to have a c in my GCF. Now, all of them actually have that invisible exponent of 1. So when you're trying to decide what exponent to put, all of the exponents are 1. So the smallest exponent you have is c to the power of 1. So even though we had 3 different variables throughout the terms, there's actually only 1 that ends up in the GCF. And that can happen, just really depends on how many variables there are and where they show up. Yep, so for this one, our GCF is going to end up being 1c. So now that we've seen GCFs with numbers, variables, and a combination of them, we're actually going to now factor by the GCF. So when we factor by the GCF, we have 3 steps. Good thing is the first step is what we've already done. First thing we're going to do is we are going to find the GCF. So what we're going to do is we're going to go through the steps as we show you an example. So in this case, our example, we are going to do 6xy squared plus 3xy plus 18. So this looks a little bit different because we have us like adding and combining all of these terms. And for instance, on the last page, we just had the terms listed. But when we find the GCF, it's going to be the same early steps. You're looking at these 3 terms. Terms are separated by those pluses or those minuses. So if we start with finding the GCF, we have a 6, the 3, and the 18. So we're going to start with those coefficients that are in front, and we want to find the GCF. Now, for our coefficient of 6, the numbers that can divide 6 are going to be 1, 2, 3, and 6. 3, it's a pretty small number, only 1 and 3 go into it. 18, we have 1, we have 2, we have 3, we have 6, 9, and 18. So again, we want to find, even though there's now 3 lists, we want to find the biggest number that is in common on every single one of these. And all of them actually have a 3. They also all have a 1, but 3 is bigger than 1. So we're going to say that for our GCF, we have a 3 in it. And again, just looking at the number part to start, and then we can go ahead and look at the variables like we were doing earlier. So then looking at the variables, remember you need a variable to be in every single term. Now, in this case, I have x's in the first 2 terms, but not in the third, so x is not part of your GCF. And similarly, I have y's in the first 2 terms, but no y in the last term. So actually, your GCF is just 3. You're not going to have any variables that are with it. And so even though there were variables in this expression, it is okay that there's not one in your GCF. It just depends. So we found the GCF. The next thing that we are going to do, so now our step 2, we are going to divide each term by this GCF. Because really, your GCF is the greatest common factor, and factor is talking about you being able to divide those terms. So it's a natural next step that we are going to take this GCF and we're actually going to divide it to all those. So what you want to do is there's 3 separate terms. Again, terms are separated by pluses and minuses. Each one of them we are going to write and like create a fraction, and on the bottom it's going to be divided by our GCF, which is our 3. So that is where the 3 on the bottom is coming from. And from here, you want to divide each fraction 1 at a time. So we have 6 divided by 3, that gives us a 2. We do have variables on the top of the fraction. There is no variables in the GCF, so all of the variables that were already there are just going to tag along. They do not get changed. So we have a 2xy squared. 3 divided by 3 gives us 1. So we'll have plus, I'll put the 1, x1 times xy. You don't need to put the 1. You could just put plus xy. And then 18 divided by 3 gives you 6. Now, a very good heads up, when you're picking the GCF, you are purposely picking something that is supposed to be able to divide every single term. So if you're ever getting to this step where you're dividing and getting something out of it, you should never have a fraction left in it because your GCF should nicely divide every single one of those terms. So we went ahead and we divided. Now our very, very last step, when we are factoring, we want to rewrite our expression as a product or as some things being multiplied together. So we are going to rewrite as a product. Now, what we're going to be multiplying together, because right now I don't see anything being multiplied with all of this. We're going to rewrite it as a product with the GCF on the outside. Now, the reason that that's going to work, what we really did here, we started with our problem and we divided everything by 3. But when you're factoring, your end answer actually needs to be, or needs to mean the same thing as what you started with. So when we factor, it's asking what times what gives you this original thing that we started with. Exactly. And so we divided everything by 3 and got this. So if you wanted to get back to your original answer, you need to take everything that you just got. I'm going to put it parentheses. Yes, it's going to be a lot of stuff in the parentheses. And your GCF of 3, I'm going to go ahead and highlight that in the same blue so you know where it's coming from. That same GCF is going to hang out on the outside because if you were to take this 3 and multiply it back out or distribute it, you would actually end up with the answer you started with, which is your goal. The biggest thing people do is sometimes they do all of these steps and they get this part, but they forget to put the 3 in the front. The 3 is there to make sure that this has the exact same meaning as the expression that we started with. If we forget the 3, we have almost all the steps, but it doesn't have the same meaning anymore. So this is actually going to be our final answer. So for our last example, we're going to factor by GCF again. It's going to be a little bit more complicated, but we're going to use the same steps. First thing, we are going to find the GCF of these 3 terms. Again, terms are separated by pluses and minuses, so that's how you know where one term starts and the next one ends. So we're going to start with, we have a 2, an 18, and an 8. We're going to start with writing down all of the numbers that go into these to find the GCF of just the numbers before we look at the variables. Now, 2 can be divided by 1 and 2. 18 has a lot more. We have 1, 2, 3, 6, 9, and 18. And then 8, a little bit smaller. We have 1, 2, 4, and 8. And just a quick note, we keep making this list because we have found it is so helpful for people. If you're someone where you're seeing, oh, did not want to erase that, where you're seeing these numbers and you already know in your head which one is the biggest one, you don't have to write out the table. However, it's just a really helpful way of doing it. Yeah, this gives you a way to, if you're someone where you like seeing everything on the page, gives you something to reference. And then looking for all of this, we want to find something that all 3 lines have in common. They all have a 1, but they also all have a 2. And the 2 is the biggest thing that all of them have in common. So that is going to be the number part of your GCF. So we have a 2, and then we'll have to see what variables, or if any, are also in the GCF. So, like we were looking on the last one, you need to have a letter in every single term for it to be in the GCF. I have an X in the first and second term, but there's no X in the last one. So X is not in the GCF. Then looking at Y, Okay, in this case, I do have y's in every term. So there's going to be a y in your GCF. And remember, the way to know what exponent it gets is to compare the exponents and take the smallest exponent, which in this case is the exponent of 2. So you're going to also have y squared in your GCF. So we have GCF, we're good. Now we're looking at step 2. We have to divide each of these 3 terms by that GCF of the 2y squared. So we're going to divide here by 2y squared. It's really like we're making 3 separate fractions. And if you want to, you could make this into 3 separate problems and break it apart a bit. It tends to be a little bit easier, just we already have all of the terms written here to put them right up there. Organizational wise, you can do it a lot of different ways. Now, for this part, we are going to be using a lot of steps that are seen in exponent rules. In particular, what we're about to do with each of these fractions is actually using the quotient rule. If quotient rule is something that you're still a little unfamiliar with, we do have a video on quotient rule. I would highly recommend that you check it out. So we're gonna go chunk by chunk. First things first, 2 divided by 2 just gives you a 1. So I'm gonna put the 1 there. Again, because it's a 1, you don't have to put it. I'm going to just make it clear. We have an x squared on the top of the fraction. There's no x in the bottom of the fraction. So we're going to keep that x squared because there's no x on the bottom that's going to interfere or change the x squared that was on the top. We have y cubed divided by y squared. Reminder, we are using the quotient rule because we are dividing these variables that have these exponents. We're going to have to do the top exponent minus the bottom one. 3 minus 2 gives you 1, so we have a y to the first. We go to the next term, do the same thing. We have a negative 18 divided by 2. That gives us a negative 9. Same idea as the last one. There is no x term on the bottom of the fraction, but there is 1 on the top, so we don't have to change it. It's going to stay that x. We have y squared divided by y squared. What we're going to end up with, from the exponent rules, we have 2 minus the 2. We actually end up with a y to the 0. Now, for that y to the 0, when you have that, you could leave it. I will say most people tend to not want to include the y to the 0 because that exponent of 0 is telling you how many times you're multiplying that variable. If you have y to the 0, that means that you are multiplying y 0 times, so you actually don't even have to include it. What a lot of people will do is if they see it in a problem here, they will say that the y squares cancel out and cross them out to get rid of them. Those all have the same meaning, so whichever way makes the most sense to you. And then keep going. We have 8 divided by 2, and that's going to get us that positive 4. And then, oh, okay, again, I have a y squared on top and bottom, so those are going to cancel out and leave us with no y's. So from here, we went ahead and we divided every term by our GCF. Be very careful. This is not your final answer because we need to have this where it has the exact same meaning as the problem we started with, and those are very clearly not the same. So for the last step, we are going to pretty much the only thing we have to do is tag something on extra. We are going to take the GCF and we're going to put it in the front. We're going to make sure this GCF is being multiplied with all of these terms. So we're going to now multiply. So you're going to put everything in those parentheses, and then we're going to have a 2y squared in the very front. Again, this just means the 2y squared gets multiplied to all 3 terms, and that does have the exact same meaning as what we started with. So one thing that I personally like about factoring is when you get here, you could actually sit there and take that 2y squared, distribute it out, and it should get you the exact problem that you started with, and that's a really great way to check your answer. So there we go for that one. Thanks for watching! If you enjoyed this video, please like and subscribe. If you have any other topics you want us to cover in later videos, leave us a comment below. We'll see you next time!